Now let's also do a few practice problems of relating to the number of the moles. So suppose you have 4.48 moles of iron and you need to see how many atoms you have in that sample. Okay, so remember that this is going to relate to the Avogadro's number, right? So remember the Avogadro's number is 6.02 times 10 to the 23rd. And so this tells us how many atoms, or anything, in this case we're talking about the atoms of the iron, how many iron atoms we have in 1 mole. So we need to find the number of the atoms in 4.48 moles of the sample. So what we can do is we can write down that in 1 mole of the iron, we have 6.02 times 10 to the 23rd atoms. And then we write down that in 4.48 moles, we have X atoms, so some unknown number. Then X is simply going to be the product of these two. We just need to multiply and then divide by 1, but of course that doesn't change the number. So if we multiply these two, we have 6.02 to 23rd times 4.48. And so that's 2.7. So I'll keep the significant figures here as it is. So I have 3 significant figures. 2.7 times 10 to the 24 atoms. That's how you can find the number of the atoms in the sample that is given in moles. You can also use the dimensional analysis, right? So to find the number of the iron atoms, let's put it this way, with a capital N, we can start with the moles. So we can put 4.48 moles times the fraction, and then on the bottom now we need to have the moles, so I can put that 1 mole of the sample contains 6.02 times 10 to the 23rd atoms. I cancel the moles. Okay, now we have a practice problem here that is asking us to find the number of the atoms, and this time it's copper, but it's not changing anything as far as the principle of this, and it tells us that the sample is 31.78 grams. So in the last problem, remember what we did is we had the number of the moles, and to find the number of the atoms we went here using the Avogadro's number, right? So we are one step back here, we are one step behind. Instead of having the moles, we have the mass. So our number one thing to do here is to go from the mass to moles, and once we have the moles, we can find a number of the atoms. And so again, this is a reminder exercise. Remember, how do you find the moles from the mass? One way was using the formula. Moles is equal mass divided by the molar mass. And so that will be 31.78 divided by the molar mass of the copper, which was, I think it's 63.5. I may not remember it exactly now. You can check. So this is grams per mole, and that will tell us the number of the moles. So let's see what we get. 31.78 divided by 63.5. Okay, and that gives us 0.5 moles. I have 2 zeros after this, so I'll just round off and say that this is about 0.5 moles. Okay, so now I'm here. I have number of the moles and I need to find number of the atoms. For that, again, I'm going to use the Avogadro's number. And so remember, we did it last time with dimensional analysis. In the last problem, we also did with setting up a cross multiplication function, but you can also do this. you can also use this formula as an alternative. You can remember that number of the moles is equal number of the particles, atoms, molecules, whatever it is, divided by the Avogadro's number, right? So from here, therefore, N is equal, I'm just cross multiplying these two, moles times the Avogadro's number. And so that will be 0.5 times 6.02 times 10 to the 23rd. So that's just getting the half of this. So that will be 3.01 times 10 to the 23rd. That's how many copper atoms we'll have here. Of course, you can also do the dimensional analysis way. So you can just go in one conversion, put everything, so that will look like this. So number of the atoms would be starting from the mass, 31.78 grams, times a mole of the copper weighs 63.5 grams. So when I cancel this now, I'm standing at moles. So that right now, this gives me how many moles I have. Times, now I want to get rid of the moles. So I'll put here 1 mole of the copper atoms contains 6.02 times 10 to the 23rd atoms. And this still is going to give me the same answer. So these are just alternative ways how you can do it. Find a way that works best for you. Most of the time I will be using formulas instead of the dimensional analysis. So let's say I would use this and then I'll use this one. But if dimensional analysis works best for you, then go with that. All right, so this is the answer. Now let's continue. Okay, so very similar problem. Instead of the copper now we have carbons. So go ahead and pause the video and try to do this by yourself. So you have 83.5 grams of the carbon, and you need to find how many atoms you have. Okay, and here as well, you're gonna first find the moles. So again, moles is equal to the given mass of the sample divided by the molar mass, which is 83.5 grams over 12 grams per mole. That's the molar mass of the carbon that I get from the periodic table. So let's divide. I have 83.5 divided by 12, and that's going to be 7 moles. Okay, 7 moles. And to find the number of the particles, I'm going to do moles times the Avogadro's number. So that's going to be 7 times 6.02 times 10 to the 23rd. Okay, so times 0.02. Okay, so 1 second, 7 times 2/23. So I've got here about 4.2 times 10 to the 24th atoms of carbon. All right, so that's the answer here. And in the solution, it's shown with the dimensional analysis. Again, if that's your preferred way, you can always refer to this as well. Now let's think about that. So here you have a 100-gram sample of each of these metals, magnesium, zinc, silver, and it's asking you which one has the greatest number of the atoms. So again, pause the video and try to solve this. You have 2 ways. One is going to be to calculate number of the atoms one by one using the methods that we have just done. And the other way is also, there's a shortcut, which try to think about that. So try to relate. How can you determine this? Just by looking at the molar masses of the magnesium, zinc, and the silver. All right, so I'm going to leave the first option to you, because that's going to be exactly the same as the previous 2 problems. So the copper and the carbon, you need to find the number of the moles and number of the atoms. But then you also have the shortcut. And here's the shortcut. the molar mass of the Mg is about 24 grams per mole. And that for zinc it's about 65, somewhere there. Silver is about 107. So the thing here is that the one that has the smallest molar mass is going to have the largest number of the atoms. And why is that? Because you have the formula moles are equal mass divided by the molar mass. The smaller this gets, the larger number of the moles get. If I divide the fraction by a smaller number, I'm getting a larger number here. So you increase the number of the moles, and then of course I'm also going to increase number of the atoms because it's correlation, right? So if I have more moles, then I have more atoms. If I have more dozens, then I have more eggs, more 12s, and etc. So whichever gives you the larger number of the moles is going to give you the larger number of the atoms as well. And that's the shortcut how you can think about this. Now, let's also talk about the molar mass or the molecular mass. So far, what we did in the examples was we had copper, we had carbon, we had iron, and etc., zinc. So these are just atoms. Now, we should be able to do the same thing when we're talking about molecules, right? So for example, if I have H2O, I should be able to find number of the moles, number of the molecules, number of the hydrogen and oxygen atoms, and etc. So for that, there's something that's called a molecular mass, and that's simply going to be the sum of the atomic masses of all the atoms that we have there, right? So for example, the molecular mass of the hydrogen is going to be the atomic masses of the hydrogens. I have 2 hydrogens plus an oxygen, so that's going to be 2 plus 16. That's going to be 18 AMU, atomic mass units. That is the molecular mass. Also, we have the molar mass, which we talked about for the atoms, but we have a molar mass MH2O. It's just going to be the same. It's going to be the molar mass of the hydrogen times 2, because I have 2 hydrogens, plus the molar mass of the oxygen. So again, numerically, remember, it gives you the same thing. So I have 18 grams per 1 mole. And this now is going to be called the molar mass. So when we are talking about the 1 mole sample, we're talking about the molar mass. If we're talking about just one molecule, that's going to be the molecular mass. Okay, so go ahead and try to do this. What's the molar mass of the barium nitrate? Take your periodic table, pause the video, and try to find that. So the M here is going to be, you need to be careful and need to consider all the numbers that you have in the formula. So it's 1 mole of the barium nitrate. I have 1 barium, so it's going to be M of the barium plus, now think about this, how many nitrogens we have in this representation. It's an NO3 and we have 2 NO3, so you have 2 nitrogens here. This 3 is only referring to the oxygen, so I'll have 2 nitrogens plus 6 oxygens, because in 1 NO3 I have 3 oxygens, but I have 2 nitrates, so that's going to be 6 oxygens. And we're talking about the molar masses. There's M everywhere. So the sum of all of these should give you the molar mass of the barium nitrate, which is 261.3 grams per mole. Right, so this is it. So this is the molar mass of the nitrogen. Okay, so here is just summarizing what I was saying. So remember, molecular mass and the molar mass, the difference, one is for 1 molecule, one is for 1 mole of the sample. Sometimes these are also referred to as formula weight, and it is just the same thing as the molar mass, even though this is not as common to use. So whenever you see this term, don't be just confused. Now, one more practice for you. Again, go ahead and pause the video and try to find the molar mass of caffeine. So the M of the caffeine is going to be, look at how many carbons you have. So 8 times the molar mass of the carbon. I have 10 times molar mass of the hydrogen. I have 4 nitrogens and I have 2 oxygens. So multiply, add all of this together, and you should get 194 grams per mole. Okay, so now let's do this. We have sodium carbonate, and it says that it is 1000 grams. And we're trying to find, first of all, the number of the moles. In all the molar conversions that we're going to do in this chapter and further on in the semester, this should be the easiest calculations for you. You should be able to calculate number of the moles immediately. And remember, you have one way for that, it's just a formula. Remember this simple formula: moles are equal to mass divided by the molar mass. Okay, so again, pause the video, do this calculation, and check again. So this is going to be 1000 divided by the molar mass of the sodium carbonate, which is about 100. So 106 grams per mole. So divide these two numbers. Now let's take this problem one step forward. So it says how many molecules of sodium carbonate you have in 1000 gram of the sample. Okay, so what are we going to do here? If you want to know how many molecules you have or how many atoms you have, so whenever it's asking you how many of the particles, you always need to use the Avogadro's number. And that you get from the moles. If you know the moles, then you can use the Avogadro's number and you can find number of the units, right? So molecules in this case. Now the problem is that we don't have the moles, but we have the mass. But in the previous problem, we actually did calculate the mass. So if you have the mass now, if you have the moles now from the previous problem, you only need to multiply the moles by number of the units. Okay, so this is the moles from the previous slide. So 9.43 moles, multiply by the Avogadro's number, and next, same problem, even a step forward. So now it's asking you how many atoms of sodium you have in this 1000 gram of the sample. So think about this for a moment, pause the video. And now the key here is going to be this. You need to look at the formula and remember the basics of the representation. These two here represents that you have 2 sodium atoms in one molecule of this compound. There's a 1 here that we don't show. And this means that in one molecule of this compound, you have 1 carbon atom. The 3 here means that you have 3 oxygen atoms in one molecule. So one representation of this molecule tells you how many atoms you have. Now, to know how many of these atoms you have in a gram of this sample, you first of all need to know how many molecules you have. Right? Because if it was one molecule, you could say that one molecule of the sodium carbonate contains 2 sodium atoms. Right? Just looking at this. And now, depending how many molecules of this you have here, that will give you X sodium atoms. Right? So I think it was 9.56 times 10 to the 24th, if I remember correctly. you can check this number. But if this is how many molecules of this you have, then you only need to multiply that number by 2. And that's reasonable, right? You can also think about this. Let's say you have a bike. Each bike has 2 wheels, right? So 1 and 2 here. And if you had a question, how many wheels you have in 100 bikes, you're just going to multiply by 2. And now it's the same thing here. It's asking you how many of the sodium you have in that many molecules, so you need to multiply by 2. And so if you had that many bikes, 9.56 times 10 to the 24 molecules, then to find the wheels, you're just going to multiply that number by 2, because every bike has 2 wheels. So that's an analogy that you can think about that. And then, for example, if the question was about the seat, so here the seat would have been, in this case, for example, the carbon, because you have in one molecule, you have 1 carbon. So one bike has 1 seat. So how many molecules you have, then the same number of the atoms you're going to have for the carbon. Okay, I didn't remember this number correctly. So it was 5.68, but it doesn't change anything. You just use this number here instead of 9.56. Okay, so multiplying by 2, and that should be 1.14 times 10 to the 25 atoms of the sodium atom. Very similar, right? So now it's asking you how many atoms of oxygen you have in the 1,000 gram of the sample. So again, as a reminder, you need to go from the mass to the number of the moles. From the number of the moles, you go, okay, so these are the moles. These are molecules. Once you know the number of the molecules, you need to multiply that by the coefficient. In this case, if it's asking you the oxygen, then you're going to do times 3, and you'll find how many oxygen atoms you have. It's a carbon, the same. If it's a sodium, you multiply by 2. So multiply that number, 5.68 times the 10 to the 24 times 3, and that will tell you how many oxygen atoms you have here. Now let's look at this one. It says consider a separate 100 gram sample of each of the following: H2O, N2O, and etc. Rank from the greatest to the least number of the oxygen. So this one is a bit trickier as far as finding a shortcut to see which one has the greatest number, because it's not, the number of the oxygen atoms is not the same in each molecule. This one has 1, this one has 1, this one has 2, this one has 2. And so if it was only 1, 1, 1, or it was everything was 2, you could simply find number of the moles based on the molar masses, and you can find it. Now, so in these kind of questions, don't take the shortcut, so don't get tricked. Just go simply take this sample, find number of the moles and number of the molecules, and then find number of the oxygen. So it's going to be exactly similar as we did for the sodium carbonate, going from mass to moles, moles to molecules, from molecules to number of the oxygen, depending again how many oxygen atom you have in each molecule. And that should give you this order.